Good evening, everyone. So, we'll start the session for today. Good evening, everyone. This is week 5 problem solving session. Yeah. So, this is NPTEL course Fluidization Engineering's problem solving session. So, this is me, Ankara Kartika, a PhD scholar from Department of Chemical Engineering, IIT Hyderabad. And the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. So, we have covered 4 sessions till now for covering the problems with respect to for the respective weeks content. So this is week 5 and the session will be from 6 p.m. to 8 p.m. Yeah, we'll start. So just an introduction of what we covered till now. So this is a course layout where we saw about the phenomenon of fluidization, advantages and disadvantages of fluidized beds and industrial applications of fluidized beds, and also the characteristics of solids, how it is classified, and flow characteristics and its outline in different types of fluidization, and about flow pattern of fluidization system like flow transition map, and frictional pressure drop and its models to analyze solid movement, mixing, segregation, and about gas distributor and the type of gas distribution in small and large scale industries, design of distributor, and also bubbling fluidized beds, entrainment and illustration from fluidized bed, followed by attrition mechanism and its analysis by model. In the last few weeks, we will be dealing with mass transfer phenomena, particle to gas mass transfer, and its analysis by model in 2-phase and 3-phase systems and its modeling. And last week it would be dealing with heat transfer phenomena, heat transfer between the fluidized beds and the surfaces and modeling them, and design of fluidized bed reactors, design for physical operation, catalytic system or non-catalytic system. Depending on the individual requirement or for this that specific application, its design would be different. All those would be dealt in the following weeks. So today's mainly we would be dealing with gas distribution system. So for the books and references, it is mainly Cooney and Levenspil's Fluidization Engineering, and followed by Gidaspo's Multiphase Flow and Fluidization, Continuum and Kinetic Theory of Kinetic Theory Description, and Gibilaro's Fluidization Dynamics, and at last S.K. Majumdar's Hydrodynamics and Transport Processes of Inverse Bubbly Flow. Mainly the content, the problems in today's session, it would be covered mostly from the Cooney and Levenspil. So if you have any doubts, you can refer to that book. So what we would we be dealing with in this week is that we are dealing with gas distribution system. So in fluidized beds, we all know that we pass the fluid inside the bed through a distributor. So depending on the design of that distributor, the whole thing would be affected. So to completely understand the system and how to operate it for different conditions, we need to know how or which gas distribution system is the efficient one, considering all aspects of that process. So for example, in small scale studies in fluidization, use ceramic or sintered metal porous plate distributors. This situation is ideal as they give uniform glass distribution because they have high flow resistance. And filter cloth, compressed fibers, compacted wire plate, or even a thin bed of small particles can also be used. Some of these materials should be reinforced by sandwiching between metal or wire plates with large openings. So when we are dealing with small scale fluidized beds, it is ideal to use ceramic or metal porous plate distributors, and because they give you uniform gas distribution. What we need is, sorry, it is gas distribution, not glass. uh, so for a small scale setup, it is ideal because we can use that by sandwiching it between plates, when in case of like compacted wire plate, compressed fibers and all. But when we are dealing with the industry scale operations, it is not efficient to use them. For example, because they have several drawbacks when we are dealing with industrial operations, when we are using these setups at industrial scales. So what are the drawbacks? What the drawbacks are, like they have high pressure drops. So these high, if there is high pressure drop, we need increased pumping power, which would be a major operating cost factor. So we do not want that. And also low construction strength, hence impractical for large scale use, high cost for some materials, low resistivity against thermal stresses, and possible gradual clogging by fine particles or by products of air corrosion. So yeah, this, I mean, they have these drawbacks, thus making it not feasible to use these setups at a larger scale or industrial scale operations. So it is very much essential to design the gas distribution system for a large scale operation, keeping in mind all these drawbacks. So there are various gas distribution systems. Just to give you an outline or the overview before starting the problems, so that it would be helpful for you. So the first one is perforated or multi-orifice plates. In perforated plates, as you can see in these image, I mean this image, you can see different type of distribution system. So it is like we have perforation in the gas distribution system, through which the gas can pass. So the first one would be, this one is a sandwiched perforated plate and staggered perforated plates, and this is a dished perforated plates, and this one is a grate bars. So in this one, what happens is that this is a sandwiching perforated plates, where a metal screen would be placed and it would be sandwiched between two perforated plates. And here it is a staggered perforated place where we do not have any screen in between. So here, as you can see, there is a metal screen or something, but here it is not there. So when large amount of solids also enter in the system, this one would be useful because we do not have a screen in between. So but what happens is that in these two, or there would be a need to keep support in the system to because they would not be very rigid. We need additional support, additional reinforcement in the system. So, and also what happens is that there is a chances for the gas leakage along the perimeter, that is near the walls. So when we in this one is the dished perforated plates. Here it can be used like for heavy, I mean, here it can be used when there is possibility of no reinforcement provided. So at those things it can be used. So here the system is designed in such a way that it has more orifice near the perimeter, that is here, than, and it is a few orifice at the center. So when channeling occurs in those systems, this can be used. And this is a grate bars. It is not widely used in industry. So it finds only limited use. So what would be the range of these perforations? It can be from 1 mm to 2 mm in small scale, or it can go up to 50 mm, that is 5 centimeter in the large scale, that is industries. It can go up to that. So based on the requirement of that application, it can go. And next is the tuyers and caps. So here, as you can see, there is a cap like thing which is attached to the fluidized, I mean the gas distribution system. So this would be used when the system is highly reactive, or we are dealing with high temperature systems. So here it would be like orifice would be there through which the gas passes, and depending on the movement it would be gas would be moving through. So in those systems, tuyers and caps would be used. And the last one is pipe grids and spargers. So in pipe grids and spargers, the design would be such that it would be like looking like this. So yeah, one more point over here is that it prevents the back falling, or the solids from falling back in the tuyers and caps. So next is the pipe grids and spargers. In pipe grids and sparges, there is the internal support which improve the gas solid contact. Also, it can act as a barrier or break up the growing bubbles. So these two are like having a downward gas distribution system. So it prevents the solid logging when the gas flow is stopped. So these are the things. And yeah, so depending on the gas entry region, the bubble behavior would be different. For example, as you can see, this is a porous plate distributor. As you can all see that the bubbles start forming in the smaller size in the near the distributor plate, and it keeps on growing in the region outwards from the distributor bottom distributor plate. Whereas this is a perforated plate, and here the chances are that jet-like bubbles are getting formed. Uh, and here it is a nozzle type tuer, and also here also the bubble starts forming from here, and they are like connected, like how can we say, it is getting formed and it is getting detached from the this point, and it keeps on growing in size. This is similar to that, and it is a bubble cap tuer. So in general, above the porous plate distributor, where here the condition would be such that gas velocity would be greater than the minimum fluidization velocity. So many bubbles are getting formed. So in other condition, if like in perforated plate, we'll consider it as a single orifice opening. And what happens is that here the condition would be such that minimum fluidizing velocity is maintained over this region. Whereas in the center, mm, the orifice gas flow rate would be very high. I mean, this is perforated plate, but I am saying in terms of porous plate. For example, consider this, and here it would be orifice opening. So orifice velocity, and here it is minimum fluidizing velocity. So based on that, here the bubbles would be getting formed. And this is a perforated distributor plate. Here as we can see that a jet is getting formed. This is the perforated distributor plate. So here a chain of bubbles are getting formed. For example, you can see this. A chain of bubbles are getting formed over here. And this is not a standing jet, or this is this chain of chain of bubbles are getting formed over here. For example, this forms when the gas velocity is comparatively low here, and the orifice velocity is very high. The orifice, where is my cursor? Okay, here. The orifice velocity high. This is the perforated plates. At uh, high orifice velocity, a jet is getting formed, whereas if the velocity is low, we can see a chain of bubbles. And similar to that, what happens is that when here the dead zone would be there, where particle mixing would not be taking place. So when we increase the gas velocity or the particle size or the orifice size, or decrease the orifice spacing, we can make sure that the dead zone is removed. And this is the nozzle type. In nozzle type, the jet formed would be causing large disturbance, and it causes better mixing of the particles than when we were using perforated plates for the same orifice area. So when we are using perforated plate and nozzle plate, nozzle gave better mixing for the same orifice opening. So that is the advantage of this nozzle. And for, so if dead zone needs to be avoided, we can go for this nozzle type 12. So why do we need to know this? Like if the jet length is very high, what happens is that the solid entrainment happens. So for efficient design of these nozzles, we need to know the jet penetration length. Only then we can ideally design the nozzle so that we can ensure effective mixing of the particles inside the bed. So till now we saw, or we had a quick recap of things that was taught in the lecture. So the recap was given to ensure that you people have no difficulty in analyzing the coming up problems. So we will start with the today's problem. So if you people have any doubt till now, please ask, so that it would be helpful before the starting of the problems, and once we start we can go smoothly. So yeah, we'll start today's problems. Question 1, it is asked that the shortcomings associated with laboratory scale distributor for the industrial operations: high pressure drop, high construction strength and low cost for some materials, high resistivity against thermal stresses and low cost for some materials, all the above. So what happens is that when we use laboratory scale design for the industrial scale operations, in the first slide itself we saw there are few disadvantages or drawbacks. So what they would be? The first one given is high pressure drop. what happens when there is a high pressure drop? Obviously, we know that when we are using porous plate distributors, there will be higher pressure drop than the than when used in small scale setup. So at industrial scale setup, it would be giving high pressure. When there is high pressure drop, we need to pump the gas at a very high pressure, right? So that it would be compensated. So the pumping cost is added more, like the pumping cost becomes more, so that it is one of the disadvantages. So option A is one of the disadvantages: high construction strength and low cost for some materials. What happens when there is a high construction strength? It is not a drawback, right? But then it doesn't happen that way. In the industrial scale operation, we have a low construction strength, and the material cost should be higher. So option B is a false statement. And similarly, in option C, it is given that high resistivity against thermal stresses and low cost for some materials. Uh, Logically thinking, if there is high resistivity against thermal stresses, it is an advantage, not a disadvantage. And similarly, the low cost for some materials, if it is there, it is an advantage. But again, when we are dealing with the large scale setup, the thermal stresses is very low, so that it is a disadvantage when we are dealing with the original system. So the option C again is a false statement. Excuse me. So the correct answer is the option A, that is higher pressure drop, because it would be giving us a more pumping cost. Therefore the correct answer is option A. And we'll move on to question 2. In question 2, it is given that perforated or multiporous plate distributor is laboratory scale distributor, industrial scale distributor, either A or B. And option D, it is none of the above. So what is a perforated multiporous plate distributor? Where do we use it? Perforated multiporous distributor, we saw in the previous slides, there we have a perforations in the gas distribution system, and there we have laboratory scale. There it can be used in the industrial scale setup. So for example, we can just go back and look into it. These are the perforated or multi-orifice plates, where as you can see in these slides, there is a perforation between them through which the gas passes. So it can be used in the industrial scales. So the answer is option B, industrial scale distributor. We'll go to question 3. In question 3, it is given that for the same orifice area and the gas flow, which type of distributor can cause large disturbances and give better mixing of particles? This one we saw while we were seeing the between the different things. So for example, as you can see over here, this is a perforated plate distributor and this is a nozzle type tuber. In this, the jet penetration length is very high, and so there is a dead zone formation, whereas here the dead zone formation is minimized. What are the options given? First of all, perforated plate distributor, nozzle tuber type distributor, both A and B give identical mixing, or option D, it is none of the above. As we can all see from this diagram, that it shows the bubble behavior. So here it is seen that the bubbles formation starts over here, and whereas in this the jet is formed. So the dead zone is more predominant in the perforated plate, whereas in nozzle type tuber the dead zone is minimized. So obviously the nozzle type tuber gives the better mixing of particles than the perforated plate distributor. So perforated plate type distributor is a wrong answer, and option B is the right answer. And option C, since it is given both A and B, A is a false statement, so again it is wrong. None of the above, again it is wrong, because it is option B, nozzle tuber type distributor. We'll go to question 4. In question 4, it is given the dead zone above the perforated plate shrinks with increasing orifice and increasing particle size. Sorry guys, there is a increasing orifice and increasing particle size, and increasing orifice and decreasing particle size, and option C, it is decreasing gas velocity and increasing particle size, and option D, it is none of the above. So in dead zone, above the perforated plate shrinks. With this one also we have seen over there, with increase in gas velocity the dead zone formation is decreased, and again with increase in particle size the dead zone formation is decreased, and increasing the orifice dead zone formation is decreased, and decreasing the space between the orifices, again dead zone formation is decreased. So from that we can see that increasing orifice and increased particle size is the right answer. Increasing orifice and decreasing particle size is the wrong answer, because we should not decrease the particle size. And option C, it is decreasing gas velocity and increasing particle size. Again, it is a wrong statement, because we need to increase the gas velocity. Although the increasing particle size is the right answer. So option D, none of the above. Since A is the right statement, A is the correct answer. Increasing orifice and increasing particle size. We'll go to question 5. The main advantage of bubble cap distributor are lower pressure drop, maximizes weeping, higher pressure drop, none of the above. So what happens is that it lowers the pressure drop. Bubble cap distributors lowers the pressure drop and it minimizes weeping. It does not maximize it. So the answer to this particular problem is the main advantage of the bubble cap distributor are lowers the pressure drop. This one is the right answer, and it doesn't maximize whipping, it minimizes whipping. It is a lower pressure drop, so option C is the wrong answer, and option D, it is none of the above. So the answer to this particular problem is lowers the pressure drop. Question 6. Which distributor is cheap and easy to fabricate? Perforated plate distributor, TUS type distributor, bubble cap distributor, all the above. So we know that, look into the picture itself. The picture speaks more than that. Perforated plates are just sandwiching the screen between two perforated plates or getting staggered formation of the perforated plates. It is easier to construct, right, than compared to tuyeres and caps, where it is seen that we have to make this and we need to make the cap, bubble cap and slit nozzle type, everything. So tuyeres and caps, it is very difficult to construct, and pipe grids. So on seeing them both, we can see that it is TUS type distributor and bubble cap distributor, both are very difficult to construct, whereas perforated plate distributor is easier to construct comparatively. So the answer is option A, that is perforated plate distributor is cheap and easy to fabricate, because in TUS and cap, TUS type distributor and bubble cap distributor, we need to make the setup. Like for example, as we can see that in TUS type and all, it would be like this. On closer look, it would be looking like this. So we need to design them accordingly so that the design is perfect one, and it does not leave out anything. For example, how it would look like, in the sense there would be a small opening for the gas to pass through, the orifice opening, and here would be some gap, and just support thing, and here there would be cap or something. So the gas will be passing over here and then here. So obviously it is difficult to construct or fabricate this, right, compared to perforated plate where we can do something like this, and metal screen would be placed over this between them, or staggered plate without any metal screen. So it is cheaper than this. So the answer is option A, perforated plate type distributor. We'll move on to question 7. Just a minute, guys. I'll just be back. Just a minute. So in question 7, where is the pointer? Question 7, it is asked that the main disadvantages of the bubble cap distributor are difficult to avoid stagnant regions and not suitable for sticky solids, difficult to clean and difficult to modify, difficulty in avoiding stagnant regions, and expensive, all the above. We saw the bubble cap distributor, right? It would be something looking like this with a bubble cap on top. This is the gas opening. So there would be some stagnant regions where it would not be reached, and so difficult to avoid stagnant regions. This is true. And again, not suitable for sticky solids. Think about what happens if the sticky solids get stuck over here, there, and all. So it becomes difficult to handle them. So not suitable for sticky solids is again true. Difficult to clean and difficult to modify, it is again true. Because modification we cannot do, right? In the perforated plates it was easier, because there was only perforated plates and with sandwiching, so we can be removing it and modifying it, whereas here the fabrication involves a very pretty much larger thing, and it was needed to if needed to clean and modify, removing this and modifying it is a very difficult task. And again, difficulty in avoiding stagnant region is true. And yeah, it is expensive, right? In the last question itself we saw which one was the comparatively cheap and easier to fabricate. It was perforated plate distributor, whereas bubble cap distributor, it is very difficult to distributor. It is expensive and difficult in avoiding stagnant regions, and it is difficult to clean and difficult to modify, so it is not suitable for sticky solids. So answer to this problem is all of the above. Option D is the right answer, that is all the above. I hope this is clear. Now we will move on to question 7. Sorry, question 8. In question 8, it is given that which type of distributor prevents solid from falling through the distributor. Perforated plate distributor, how it would be designed would be looking, it is like this. I mean, think of some perforation with screen in between or no screen, something. Nozzle type distributor, we have something like nozzle in the distributor. And bubble cap tier type distributor, we have something like this with some bubble cap. So, which one do you think would be ideal to use when to prevent backfall of the solids? So here the chances of solids falling through is higher. Here also chances of solids falling is there. But here the backfall of solids is very less compared to the other things because it closes up and it only opens for the fluid. So bubble cap tier type distributor is the right answer. It is not perforated plate distributor or it is not nozzle tier type distributor, it is bubble cap tier type distributor. And because it opens and closes on the arrival of the gas or the fluid, so this one is the ideal one, and option D, it is none of the above. Again it is false because answer is option C, bubble cap tier type distributor. We'll go to question 9. Read this question and we'll discuss the answer. For the porous plate distributor, to maintain uniform fluidization, the pressure drop is related to the fluid velocity, such as a required pressure drop is directly proportional to the fluid velocity. Option A. Required pressure drop is inversely proportional to the fluid velocity. Required pressure drop is proportional to the square of the fluid velocity. So the main thing to be noted is porous plate distributor. Here the question is about porous plate distributor. So the pressure drop, how it would be, how it is related to fluid velocity, u naught. Let's keep it as u naught. So option 1, it is directly proportional. So this one is the right answer. For porous plate distributor, delta P is directly proportional to the fluid velocity. So the answer to this is option A. For perforated plate distributor, if the question is about perforated plate distributor, the question is about the pressure drop is directly proportional to the square of the velocity, fluid velocity. So in that case, for perforated, the answer is this. Option C. But for now, the question is about porous plate distributor. So the answer is required pressure drop is directly proportional to the fluid velocity. For example, the pressure drop across the distributor is directly proportional to u naught. I hope this is clear and this makes sense. Just keep in mind, for porous plate distributor, it is directly proportional to the fluid velocity. For perforated plate distributor, the fluid velocity, the pressure drop is directly proportional to the square of the fluid velocity. We'll go on to question 10. The jets will not contribute much to bed stirring and bubble rising when the alpha factor is alpha less than 1, alpha greater than 1, alpha is equal to 1, alpha is equal to 0. So what is alpha? Alpha is the measure of the stirring effect. So in general, it is used in the agitated distributor. For example, when we are dealing with the fine solids, right? At that time, it is not only sufficient to go with the distributor. Again, some other additional factors must be needed to ensure the proper mixing of the solids. So in that case, we use the alpha. Alpha is nothing but it is the ratio of the kinetic energy of orifice jets. Alpha is nothing but kinetic energy orifice jets by bed resistance. So on thinking that, we'll just see jets will not contribute much to bed stirring and bubble rising when the bed resistance is more. So kinetic energy of orifice jets would be low in that case, and the bed resistance would be more. Only then the jets will not contribute much to bed stirring effect on the bubble rising. So in that case, if the bed resistance is bed resistance is high, what happens? Alpha becomes very low. So answer is option A. In other cases, alpha is greater than 1, the jets will be contributing something or the other to the system. We'll go to question 11. For the porous plate, okay, actually it is a similar question. For the porous plate distributor, to maintain the uniform fluidization, the pressure drop is related to the fluid velocity as the pressure drop is directly proportional to the fluid velocity, inversely proportional to the fluid velocity. Required pressure drop is proportional to the square of the fluid velocity. Same question as question 9. So the right answer is required pressure drop is directly proportional to the fluid velocity. For the porous type distributor, the required pressure drop is directly proportional to the fluid velocity. It's the right answer. Again, this is a similar question. I don't know why the questions are repeated with some wordings. I mean, some different wordings. So, if the factor alpha measures the stirring effect is lesser than 1, the jets will punch right through the bed, causing severe gas bypassing, attrition of particles, and erosion of bed materials. Jets will not contribute much to the bed stirring and bubble rising. There is no particular jet formation. Option D, it is none of the above. So we all know that alpha or the stirring effect is the ratio of the kinetic energy of the incoming jet orifice jets to the bed resistance. So if alpha is lesser than 1, what happens? The bed resistance is more. So in that case, what happens? The bed resistance would be more. The jet would not be contributing much. So the answer is option B. The jets will not contribute much to the bed stirring and bubble rising. It will not punch right through bed, causing severe gas bypassing or attrition of particles, because it is obviously lessened by other factors. So this was a question similar to the question 10. So here it is asked that jets will not contribute much to this bed stirring and bubble rising when the alpha is lesser than 1. It is the measure of stirring effect, because we already saw that when we are dealing with the finer particles, it is not only sufficient to use the proper distribution system, it also becomes necessary to use additional support to ensure the particles get how to say, the particles get mixed uniformly. So in such cases, we ensure that have an additional agitator or additional stirring. So in order to measure that efficiency, we use the term alpha, measures the stirring effect. So if it is lesser than 1, obviously it would not be contributing much to the bed stirring and the bubble rising. So yeah, before moving on to question 13, we'll just take a 5 minutes break and we'll meet again sharply at 6:55. Thank you. So yeah, we'll just start it is about question 13. In question 13 it is asked that the ratio specific heat capacity for the monatomic gas is 1.33, 1.40, 1.67, 1.85. So the right answer is option C, 1.67. So we'll see how that is the right answer. Uh, what is the specific heat capacity ratio? It is Cp by Cv, right? So for Cv, what does Cv means? Can anyone answer? It is the heat required to raise the temperature of 1 mole of the gas by 1 degree Celsius. Sorry, it is the heat required to raise the temperature of the 1 mole of gas by 1 degree Celsius. So what at constant volume? If it is Cv, it is constant volume. If it is Cp, it is constant pressure. So Cv for monatomic gas is F by 2R, where F is the degree of freedom. For monatomic gas, F value is 3. That is, it has only 3 degrees of freedom. That is, only translational degrees of freedom is available for monatomic gas. So F is 3. So Cv is 3 by 2. 3 by 2 R. And Cp is nothing but Cp is minus Cv is equal to R. Cp is equal to Cv plus R. So Cp is equal to 5 by 2 R. R is the gas constant. So what is the specific heat capacity ratio? It is nothing but Cp by Cv. Cp is 5 by 2 R divided by 3 by 2 R. So what happens? 5 by 3, it gives 1.67. So option, I don't know. Option C, 1.67 is the right answer. How is it? For this is the question is about monoatomic gas. So we know it to be ratio of Cp by Cv. Cp is nothing but Cv plus R, and Cv is nothing but for the heat required to raise the temperature of 1 mole of a gas by 1 degree Celsius. So for monoatomic gas it is 3 by 2R, that is F by 2R. So on substituting it there, we get the Cp as 5 by 2R. So Cp by Cv would be 5 by 2 by 3 by 2. RR gets cancelled, 2 gets cancelled, it is 5 by 3. It is 1.67. We'll go to question 14. For real operations with frictional losses, the actual shaft work is always smaller than the ideal, always greater than the ideal. Option C, it is always equal to the ideal. Option D, it is none of the above. So we know that for real life operations, the actual would be ideal divided by the efficiency. Since efficiency is always lower, it is not equal. In that cases, the actual shaft work would be greater than the ideal case. For example, where is it? We need to give more work than the ideal case because frictional losses would be there. The loss to compensate that, we need to give more work. So the actual shaft work is always greater than the ideal. That is option B is the right answer. Oh, sorry. It is option B. You you will understood, right? Option B is the right answer. For an axial blower of a two-stage reciprocating compressor, the compressor efficiency is roughly given by 0.8 to 0.9, option A. Option B, it is 0.6 to 0.8. Option C, it is 0.55 to 0.75. Option D, it is 0.45 to 0.65. Option A, it is the right answer. That is option A, 0.8 to 0.9 is the right answer, because the question is about for an axial blower of a two-stage reciprocating compressor. For other things, what would be the case? It is given over here. If it is 0.55 to 0.75 for turbo blower and zero point 0.6 to zero point 0.8 for a roots blower, zero point 0.8 to zero point 0.9 for an axial blower or a two-stage reciprocating compressor. So the question is about axial blower or a two-stage reciprocating compressor. So the efficiency, compressor efficiency is between 0.8 to 0.9. We'll go to question uh, 16. Yeah. Determine the compressor power to pass the reactant gas into the plenum of the fluid bed system. P1 is 101 kilopascal, P2 is 388 kilopascal, volumetric flow rate of fluid is 10 meter cube per second, efficiency of the compressor is 90%, ratio of specific heat capacity is 1.4. Option A it is 19,927 kilowatt, option B it is 1,820 kilowatt, option C it is 1,727 kilowatt, option D it is 1,620 kilowatt. So the right answer is option B, 1,820 kilowatt. So we'll see how to solve this problem. Uh, what is the first step that we always do? We write the given. So similarly, we'll do that. What is given? Determine the compressor power to pass the reactant gas into the plenum of fluidized bed system. So to find it is the compressor power. Reactant gas into the plenum of the fluidized bed system. So what is the given? It is P1 is 101 kilopascal, P2 is 388 kilopascal, volumetric flow rate of fluid is 10 meter cube per second, efficiency of compressor is 90 percentage. We'll also insert this for future. Yeah. Efficiency of the compressor is 90 percentage. Ratio of specific heat ratio gamma is 1.4. We'll keep it Q. we'll write the formulae. Minus W is equal to it is gamma by gamma minus 1 gamma divided by minus 1 P1 V1 it is P2 divided by P1 1. So this is the equation. The answer is what we got here. We'll keep it as V1. So it is a simple problem from now on where we need to just substitute it. W as ideal is equal to we have 1.4 divided by 1.4 minus 1 into 10 meter cube per second. Okay, sorry, it is P1 is 101 kilopascal, so it is 10 power 3. Again we got 10 meter cube per second, and in the bracket we got P2 by P1. P2 is 388 divided by 101 kilopascal. Kilopascal gets cancelled, and sorry, it is 1.1 minus 1 divided by 1.4. We got everything minus 1. So we'll just substitute these values, and what we would be getting 353500 once. One 1.4 divided by 0.4, it is 3.5, and then into 101 into 10 power 4 380 388 divided by 101, it is 3.8415. 3.8415. power to the power 0.4 by 1.4. 0.4 divided by 1.4. It is 1.4689 minus 1. So minus 1. Guys, you people also please do along with me so that it would be easier for you. Into 1 not 1. It is 1657689.75 Newton per meter square. That is what? So this one is 1657.69 kilowatt. Sorry, kilowatt. So the question was about WS actual. Is equal to 1657.69 divided by efficiency, that is 0.9. What does this give us? Divided by 0.9. 1841.8 kilowatt. So yeah, we'll see the answer. This is 1820 kilowatt. So as we all can see, that one of the option is 1620 kilowatt. It is not the right answer. Um, so the answer is compressor power to pass reactant gas into the plenum of fluid. So that we need to know the actual value, not the ideal one. P1, P2. Yeah, that's it. I hope this problem is clear to you. If you have any doubt, please ask now. It is a very simple problem where we are asked to find the actual work done by the compressor, that is the compressor power to pass the reactant gas. So we are given the inlet of the compressor pressure drop and the volumetric flow rate and the exit pressure. So we know that this we know this formula for the air case. So on substituting this, we will get the answer. Okay, we will see question 17. One more problem is there actually. Yeah. Question 17. In question 17, it is asked that bubble rise velocity exceeds its linear growth rate and increasing orifice flow bigger bubbles form above the single orifice above the perforated plate at a nozzle to none of the above. So when bubble rise velocity exceeds its linear growth rate and increasing orifice flow, bigger bubbles form. So when the bubble rise velocity is exceeding its linear growth rate and the orifice flow and increasing the orifice flow, bigger bubbles form where above the single orifice plate. In question 18, it is asked that the ratio of specific heat capacities for the diatomic gases. Previous question we saw about the monoatomic gas. Here it is asked about the diatomic gas. So what was the formula we saw? Ratio of specific heat capacity gamma is given by Cp by Cv, where Cp is nothing but the amount of heat required to raise the temperature of 1 mole of gas by 1 degree Celsius at a constant pressure, where Cv is nothing but the amount of heat required by the gas to raise its temperature by 1 degree Celsius to raise its 1 degree Celsius for the 1 mole of gas at a constant volume. So if we saw that Cv is nothing but the F by 2 of R. For the diatomic gas, we have degrees of freedom F as 5, where it includes the 3 translational degrees of freedom plus 2 rotational degrees of freedom. And on substituting that, we get FCV is equal to 5 by 2 R and Cp is equal to 5 by 2 plus R, 5 by 2 R plus R. So it is 7 by 2 R. So for gamma, it is nothing but Cp by Cv. So 7 by 2 by R, 7 by 2 R by 5 by 2 R. What does it give? 7 by 5. 7 by 5 is nothing but 1.40. So the right answer is 1.40. Options given are 1.33, 1.40, 1.67 and 1.85. But the right answer is 1.40, which is nothing but 7 by 5. Question 19. At high velocities, bubble coalesce into horizontal jets. This statement is true for nozzle tube, bubble cap tube, perforated plate, none of the above. At higher gas velocities, bubbles coalesce into horizontal jets. This is true for nozzle tube, bubble cap tube, perforated plate. In nozzle tubes only, the bubbles coalesce into horizontal jets when the gas velocity is higher. So the right answer is option A, nozzle tube. So we are yeah, this one is the last question for today's session. So this is a problem where we are asked to find the compressor power requirement. Just read this question and try solving it on your own, and we'll also solve. Yeah, what is asked is here, calculate the compressor power requirement to run an atmospheric fluidized bed coal combustor when the distributed pressure drop is 3 kilopascal. Air enters at 101 kilopascal at 20 degrees Celsius with ratio of specific heat capacities as 1.4. The pressure drop across the bed is 10 kilopascal. The pressure at the bed exit is 103 kilopascal and coal feed rate is 8 tons per hour and its gross heating value is 25 megajoules per kg. The air at standard conditions needed is 10 meter cube per kg of coal and the efficiency of compressor is 0.75. So what is the compressor power requirement? 455 kilowatt, 655 kilowatt, 355 kilowatt, 200 kilowatt. So So just read this question and do as we always do, like write the given first and write the formula and then substitute it in the formula. uh, think for 2 minutes and then we'll discuss the answer. So yeah, we'll start with the problem solving. um, okay. So basically what is asked is that we have a compressor here and it is passing the inlet gas into the fluidized bed. So we have 103 kilopascal at this region. Mm, so this is the gas distributor plate. The exit is having the pressure of 103 kilopascal, and this is the distributor plate. Let us keep the pressure here as P2 and pressure here as P1, and it is the pressure P0, that is inlet gas velocity, inlet gas conditions at 101 kilopascal, and temperature T0 as 20 degrees Celsius. So what else is given? Pressure drop across the bed is 10 kilopascal. So as always, we just write what are all the given conditions first, and then proceed to the solving the problem. Compressor power requirement is the to find. What are all given? To atmospheric, when the distributor pressure drop is distributor pressure drop is equal to kilopascal. Air inlet is 101 kilopascal, T naught is 20 degrees Celsius, and gamma is 0.4. Pressure drop across the bed equal to 10 kilopascal. Pressure at the exit is 103 kilopascal. Coal feed rate is 8 tons per hour, and we don't need this for now. Okay. Coal gross heating 25 megajoules per kg. Air conditions standard condition is equal to 10 meter cube per kg of coal. Compressor efficiency of the compressor is 0.75. So here it is, in we'll keep it as delta PD. Delta and pressure drop across the bed is delta PB. And pressure at the exit is P3. What else? Coal feed rate is 8 tons per hour. Air is 10 meter cube per kg of coal. I hope we have given all these things. So to find is compressor power requirement. So we'll substitute these in the problem first. Actually, this is a very straightforward problem. be in this corner. So so P3 is equal to 103 kilopascal and P naught is equal to 101 kilopascal. V naught is equal to Q into M, which was nothing but Q was 10 meter cube per kg of coal. 10 meter cube per kg into 8000 kg per hour. On converting this into seconds, 1 divided by 3600. So what will we get for this? We will calculate it. 10 into 8000 into 1 divided by 3600. It is 22.22 meter cube per second. So we are given one more thing. What was that? Delta PD is equal to 3 kilopascal. Delta PD is equal to 3 kilopascal. What does it mean? It means that P2 minus P1. No, it is actually P1 minus P2. P1 would be greater, right? P1 minus P2 is equal to 3 kilopascal. And similarly, bed pressure drop is given as 10 kilopascal. Values, right? At 10 kilopascal. So what does it mean? It is P3 minus P2. So it is nothing but P3 minus equal to 10 kilopascal. So we know P3. Okay, it is P2 minus P3. Minus P3 is 10 kilopascal. So what does it mean? P2 then would be 103 plus 10, that is 113 kilopascal. So P1 minus P2 is, we'll go this way if not. P1 minus P2 is 3 kilopascal. So what is P1? P1 is equal to 113 plus 3 is equal to 116 kilopascal. So what we need to know is, to know the compressor power requirement, we need to know the inlet and the outlet condition of the fluid. So we know the inlet air condition, but we do not know how much, at what pressure it is exiting out of the compressor. So to identify the exit pressure of the compressor, we are calculating it through these means. So we know the exit I mean bed exit pressure, and we know the bed pressure drop, and we know the distributor pressure drop. So on using all these things, we are identifying it as P1 minus P2 is 3 kilopascal, and P2 minus P3 is 10 kilopascal. So adding all these to the exit pressure, we are arriving at the exit compressor's exit pressure, that is 116 kilopascal. That is compressor exit pressure is 116 kilopascal. So at this point we know what is P naught, what is, so we'll just keep the required things. And we need to know the V naught. Yeah, P naught, V naught, P1. Yeah, that's it, right? So we know the formula from the previous problem itself. One more problem we saw, right? So we know the formula. So we know W S ideal is equal to gamma, it is given 1.4 by 1.4 minus 1 P1, that is here it is P naught V naught. So yeah, we'll what is P naught here? It is 101 into 10 power 3 into 22.22. So and then we are having this 116 by 101. 1.4 minus 1 divided by 1.4 minus 1. So we'll substitute all these and we'll see what answer we are getting. 1.4 by 1.4 minus 1. 1.4 divided by 0.4. It is 3.5. Yeah, it is 3.5. It is 7 by 2, right? Into 101 into 22.22. It is 2 2 4 4 2 2, and then it is 116 divided by 101 into 1.14851, 0.4 divided by 0.4 divided by 1.28571. 57 minus 1. 1.14851 power 0.2857. 1.14851 power 0.2857 minus 1, that is giving 0.5 into 2244220 into 0.0404. So that gives us 3.5. Something is wrong actually. Okay, yeah, I found it. It is given that 22 meter cube per second. So this one is at V0 initial condition at 20 degrees Celsius. At 20 I mean, it is given at standard condition. At standard condition. So at 20 degrees Celsius, how much it would be? So V1 by T1 is equal to V2 by T2. So V1 is equal to V2 by, that is 22.22 by what is this? This is 273 at 20 degrees Celsius. So we need to multiply it by 293. So the answer is 293 divided 273 into 20. It is 23.85 meter cube per second. this into 101 would give us 240. 863. So 240 863 into 3.5 into 0.01 240 863 into 0.0404 into 3.5. Something is going wrong. Just a minute. Point. Okay. This one is 340.24 kilowatt. But we know that to get the actual value, we would divide it by 24 divided by 0.75. That is giving us 453.65. 454 kilowatts. We'll see what the answer is. 455 kilowatts. Yeah, the answer is right. So here again we should see that another option 355 kilowatts is given. So in case if we are stopping without getting it the actual one, we might get the wrong answer. So we'll just go through the problem once again. What is asked is to calculate the compressor power requirement. What is given is compressor inlet conditions are given. P0, P0, T0, everything is given, and the exit of the fluidized bed is at pressure of 103 kilopascal. We know the pressure drop of the bed and pressure drop of the distributor. So from that we need to calculate the exit pressure of the from the compressor. So we add up all these things like 103 plus bed pressure drop of 10 plus 3. 113 plus 3 it gives us 116 kilopascal. So the pressure from the outlet gas from the compressor is 116 kilopascal. That is the inlet to the bed is at a pressure of 116 kilopascal. So we know it as 116 kilopascal, and we know the we calculate the volumetric flow rate at the condition of 20 degrees Celsius. So it is 23.85 meter cube per second, and then it is a simple substitution where we substitute it in the given formula and calculate the ideal and divide it by the efficiency of the compressor to get the actual value. So thank you guys. These are the problems for today's session. If you people have any doubt, please ask. So just a quick recap of what all we saw in today's session. Today's session is about gas distribution system in the fluidized bed. So it is perforated multi-orifice plates, skewers and caps, and pipe grids and spudges. We saw an intro of that and bubble how behavior in the with different types of gas distribution system, and about we saw the gas distributor and the theory questions behind them, and the dead zone and what type of distributor is used where and how what are the disadvantages with them. We all saw them, and also we saw about the stirring effect when measure, that is alpha, and how jet size is depending on it, and how the system behavior is influenced by that. And further we saw the pressure drop factor and heat capacity we calculated for monoatomic and diatomic gas. And we saw a problem wherein we calculated the compressor power requirement, where the formula is actually this, that is Ws ideal is equal to gamma by gamma minus 1 P1 V1 into P2 by P1 to the power of gamma minus 1 by gamma minus 1. So this would give us the ideal power requirement, and we should divide it by the compressor efficiency to get the actual power requirement. So actual would always be greater than the ideal, because we need to account for the friction losses also. We saw the problems for that, and one more problem also we saw from in this problem. In addition to the compressor power requirement, we saw how the pressure drop across all these things is influencing the compressor exit. I mean, compressor exit gas is pressure drop happens because of distributor and the bed. So how it is influencing we saw in this problem, and we added up everything together to get the compressor power requirement. So these are all the problems for today's session. I thank everyone for attending. If you people have any doubt, please ask now. I'll be happy to take questions now. It is 7:54, so we'll wait for 5 minutes, and then we'll close the session. So the next class is on next Friday from 6 p.m. to 8 p.m. So if you have any doubts from this session, you can always ask in the next session also. Thank you guys for attending. Yeah. If you have any doubts, we can ask, or else we can close the session. Okay, I guess there is no one here to ask question. So yeah, thanks everyone for attending today's session. We'll meet again in the next week in the same time, 6 p.m. to 8 p.m. Since no one is there, we'll close the session. If you have any doubts, you can always ask. Thank you guys.